This is the demo for Class 21 for college algebra. We've already studied the concepts and applications of two polynomial functions. We didn't call them polynomial functions, but they are. Linear functions, like y equals mx plus b, and quadratic functions, which we did in the previous lesson, y equals ax squared plus bx plus c. Okay, so lines are degree 1 because the power on x is a 1. If you write y equals mx plus b, there's a little 1 on that x for the exponent. And then for quadratics, we had y equals ax squared plus bx plus c. And we call that quadratic or degree 2 because the highest power on x is a 2. So we're going to expand our study of polynomial functions today. We're going to start with the definition. So the definition is just coefficients times x to a power. Okay, so these a's are just coefficients, okay, on x to a power. So we have a constant, like the b and the c in the line and the quadratic. This is our constant term. And then we have a linear term, a coefficient times x to the first, a quadratic term, a coefficient times x squared, and then it just keeps going up and up and up until we have a coefficient times x to the n, and n is just the highest power of x that is in this particular polynomial. A sub n, the coefficient on the highest power of x, we call that the leading coefficient. So here's an example of a polynomial function. F of x equals 11x cubed minus 6x squared plus x plus 3. Identify the degree, the leading coefficient, the leading term, the constant term, and the domain. Okay, so the leading coefficient, that's the coefficient in front of the highest power of x. So that would be 11. The degree is the highest power you see on x, which in this case is 3. The constant term, that's the term with no x's, it's the 3. And the leading term is the entire term, not just the leading coefficient, but the leading term. So that includes the x cubed as well, 11x cubed. And the domain of any polynomial function is going to be negative infinity to infinity. You can plug any x in here that you want. There are no restrictions. There are no fractions where you want to avoid a 0 in the denominator. There are no square roots. You can cube any number, you can square any number. So the domain for this polynomial is all real numbers, negative infinity to infinity. Polynomial functions of degree 2 or higher have graphs that are smooth curves, no sharp corners, and they don't have any breaks. Okay, so smooth curves, they don't have any breaks or sharp corners. So we want to circle the graphs below that represent polynomials. So we can eliminate anything that has a sharp corner or a break, and what's left look like polynomials. Consider another polynomial function. F of x equals x plus 3 times x minus 2 squared times x plus 1 cubed. So this is a polynomial function written in factored form. It is completely factored, meaning it's written as a multiplication problem. So I want to look at the behavior of this graph at the x-intercepts by examining the multiplicities of the zeros at -3, 2, and -1. Okay, so let's begin our examination of the graph's behavior at this x-intercept at -3, 0. So it goes through the x-axis right there. We call x equals -3 a 0 of the function because if I wanted to find the zeros, I would set f of x equal to 0. And because I have it written as a multiplication problem, I can set each factor equal to 0 separately. And when I set x plus 3 equal to 0, I get x equals -3. So that's how I find the 0 or the x-intercept. So if you look at the graph near that x-intercept, like just a little box around it, and imagine zooming in just on this little box, what you might notice is that where the graph passes through the x-axis looks very much like a line. It looks like it's just a straight line. Goes straight through the x-axis and kind of looks like a line. So the factor x plus 3 is linear, It has degree 1. There's a little hidden 1 on that x to the first plus 3. So the behavior near this x-intercept looks like that of a line. This looks like a line because x plus 3 is linear. Passes directly through the x-axis in a linear fashion. Since there's only a single factor, x plus 3, it's not squared or cubed or raised to any power, it's just x plus 3 to the first, we say there's a single 0, or the 0 x equals negative 3 has a multiplicity of 1. So I'm going to use this information to fill in this chart. So I have an x-intercept at negative 3, 0, which means that my 0 is x equals negative 3. Behavior near the x-intercept is it goes through the x-axis and looks like a line. And the multiplicity of that 0 is 1, because we only have to set x plus 3 equal to 0 one time. Okay, my other x-intercepts. I have another one at negative 1, right here. So I have an x-intercept at negative 1, 0. My 0 is x equals negative 1. Okay, because I need to set, that happens when I take x plus 1 cubed and set it equal to 0. Write that over here. X plus 1 times x plus 1 times x plus 1 equals 0. That's what it means, x plus 1 cubed. It's x plus 1 times itself 3 times. So when I set each of those factors equal to 0, I get x equals negative 1, and negative 1. 3 times. That means the multiplicity of that 0 is 3. So the power of 3 there means 3 factors of x plus 1, which means that the 0, x equals negative 1, happens 3 times. We call that the multiplicity. And then if I want to describe the behavior near the x-intercept, put a little box around this and imagine zooming in. It goes through the x-axis, but it kind of flattens out near the x-intercept, and it kind of looks like x cubed. So this goes through the x-axis and looks like y equals x cubed. Okay, third x-intercept happens here at x equals 2, or negative 2 comma 0. Okay, and the way we would get that 0 is setting this factor, x minus 2 squared, equal to 0. That's x minus 2 times x minus 2 equals 0. Set each factor equal to 0, and I get x equals 2 times, because there were 2 factors, because x minus 2 was squared. So my multiplicity of that 0 is 2. Sorry, that's positive 2. So my multiplicity of x equals 2 is 2. That's a 0 2 times. And what does it look like? Well, this time it doesn't go through the x-axis. It bounces off the x-axis. And if I were to draw a little box around here and zoom in, it would look like x squared. So this bounces off the x-axis. And looks like y equals x squared. And it looks like x squared because it was multiplicity 2, had a squared on it. So to summarize what we saw in the last example, the multiplicity of a real 0 tells us about the graph's behavior near the x-intercept. If the multiplicity is even, like in the case when it was 2, then the graph bounces off the x-axis at the 0. If the multiplicity is odd, the graph crosses the x-axis at the 0. And if the multiplicity is 1, then the graph crosses straight through the x-axis, looking like a line. If the multiplicity is odd but greater than 1, then the graph flattens out as it crosses the x-axis. The sum of the multiplicities is the degree of the polynomial. So the degree of this polynomial function is the sum of the multiplicities. So x equals negative 3 had a multiplicity of 1, x equals 2 had a multiplicity of 2, and x equals negative 1 had a multiplicity of 3. So the degree of this polynomial is 6. In order to determine the multiplicity of a 0, you do have to have your polynomial function in factored form. Okay, and it will be the power on each factor that determines the multiplicity. Number 6, the leading coefficient test. As x increases or decreases without bound, that is, as x goes towards infinity or to negative infinity, the graph of the polynomial function eventually rises or falls. So if this is our polynomial function, remember n is the degree and a sub n is your leading coefficient. When your leading coefficient is positive, your graph rises to the right. Okay. So in both of these cases where your leading coefficient was positive, your graph rises to the right. If the degree is odd, then it rises to the right and falls to the left. When n is even, the degree is even, and the leading coefficient is positive, it rises to the right and to the left. Okay. If your leading coefficient is negative, your graph falls to the right, so falls to the right, falls to the right for negative leading coefficients. And when n is odd, the right and the left do opposite things. So n odd, leading coefficient positive, we have falls to the right, rises to the left. And if n is even and the leading coefficient is negative, it falls to the left, falls to the right. This is our notation for describing end behavior. So for this picture, we say as x approaches infinity. So as your x values move to the right, f of x, or the y values, go up. So as x goes further and further to the right, the y values get bigger and bigger. They go towards infinity. And then we say as the x values move to the left, as x goes to negative infinity. So as x goes to the left, what's happening to the y values? They are going down to negative infinity. Determine the end behavior of our factored polynomial that we were looking at previously. We analyzed what's happening at its x-intercepts. Now we want to use the leading coefficient test to determine its end behavior. Okay, so first I'm just going to look at the end behavior graphically. So I happen to know that the degree of this polynomial is 6. I add up the multiplicities. 3 plus 2 plus 1 is 6. So this is 6th degree polynomial. The leading coefficient, I know it must be positive because the right side is rising to the right. So I don't know, I definitely know it's positive. And in fact, if I were to multiply this all out, I would have an x times an x squared times an x cubed, which is 1x to the 6th. In fact, it is 1. Okay. The graph of f rises to the right and rises to the left. Okay, so as you follow the graph to the right and to the left, the graph is going up. So I can fill in these blanks to use correct notation. So as x approaches infinity, that means as we go to the right, what's happening to the y values? They are rising, so they are also going to infinity. And as x goes to negative infinity, that means as we move to the left, what's happening to the y values? They are also rising. They're going to infinity.